Hello. This video and this part is actually a matrix algebra. So if you're confident that you mastered everything from the matrix algebra, then you may skip this video. So I assume that you have heard about rank, linear independence, things like this, but I would like to give you more working knowledge of what is a rank of a matrix. So maybe you may remember the definition of a rank, but it is really hard to get practical working knowledge what the rank actually means. So let me try to explain what it is. So think about, as you know, a matrix is basically a system of linear equations. You write m number of equations with k unknowns. So coefficients are a11, a12, a1k to a m1, a m2, a mk. So there are m by k coefficients, and on the right hand side there are m number of constants. And then you may write this system of equations as ax equals b. It's obvious what it means, right? X is k by 1 dimension, a is m by k dimension, b is k by m by 1 dimension. And here, m is a matrix, so we can define the rank of A. And I would define this as rank of A is the number of unknowns that the system of equations can determine. How much unknowns it can determine without additional knowledge. So I'll give you more examples. So for example, in the first example, it's too simple. X plus y equals to 1. There is only one equation, and that means you can determine only one. So what you can only with this equation, you cannot say anything. You cannot say anything what is x, what is y, but if you know either x or y, then you can determine the other. Like if you know that x equals to 0, then you can determine y equals to 1, right? That's the maximum this equation can do. So the rank is 1. Only one equation can determine only one variable. So the other variable should be like assumed, or I don't know how to, anyhow, it cannot solve for 2. It can solve for only 1. The second example, x plus y equals to 1, 2x plus 2y equals to 2. Even though it looks like two equations, it's only one. So by the same logic, so basically there is no difference between the first equation and the second system. So rank is still 1. You cannot determine what's x and what is y. But as I said, when I assume that x equals to 0, you can say y is 1. Even though there are two equations, you can still handle only one unknown. And the third example, this is the typical common, the nice case, well-behaved, simple case where you have two equations and two unknowns, and two equations can solve for the two unknowns. From here, you know what is x and what is y, and so you can determine both of them. The rank is 2. And think about this. In this case, you have 3 equations but 2 unknowns. That means you have too many equations. The problem is, if you try to solve this equation, this system of equations, there is no solution. There is no solution to that satisfies the 3 equations at the same time. But what you can do here is you have one redundant extra equation. So if you delete one of them, delete any of them. So if you delete any of them, then you can determine 2. So in that sense, you can handle 2 unknowns. But the problem is, it is not clear how you determine the 2. It has enough power, but you need to think more how to use that power, or you need to suppress the power, from 3 to 2, So then how can we reduce the power? So that's what we need to think about. So then anyhow, I believe you understand what a rank of a matrix means. Basically, how many unknowns it can handle, a system of equations can handle. And then what you can learn from here is, in our regression model, we have k unknowns. Then, obviously, intuitively, a necessary condition for the solution is that you have k number of equations. So if you have two unknowns but only one equation, then you cannot do anything. So if the number of equations is lower than the number of unknowns, nothing you can do. So you cannot determine anything. So it's simple. And then a necessary and sufficient condition for a unique solution, for the solution to exist, is rank. Rank should be, so the number of unknowns the system can handle equals to the number of unknowns. So exactly, that's what it means. Now then, so this is a general idea, and let's think about 2x2 case. Back to our instrumental variable example. If you come back to 2x2 case where x1 is scalar, x2 is also scalar, and both are endogenous. To simplify, I assume both are endogenous, and I assume there are two instruments. Then this is exactly what we have done, and this can be written as ax equals b, like this, right? So the unknowns are beta 1 and beta 2, and the known is the expectations. All the expectations are identified from the data. So expectations are known, but betas are not known. Then you need to solve for this. Solve for x. Solve this equation for x. And then, as I said, the necessary and sufficient condition for the identification for the solution is this. Rank equals to 2. And this rank equals to 2 means there are many different definitions. One is, say, the columns are linearly independent, or if a matrix is square, full rank means the matrix is invertible, which is also equivalent to have a non-zero determinant. So if you learned matrix algebra, you learned all of these terms like rank, determinant, linear independence, inverse, singularity, like a square matrix. So review your textbook, but the idea is simple. You are going to get this condition. If this condition is satisfied, then the rank equals to 2, and especially in this case, because A is square, you have inverse, and the solution is unique, right? It is also fine. And now the problem is, so when you have a square matrix, the solution is pretty simple. Just take the inverse and assume that there exists, or verify the condition for the inverse invertibility. But the problem here is, what if you have 3 instruments for 2 endogenous variables? This happens in many cases, and we are going to do the same thing. Ax equals to b, so x is beta, and a and b are expectations. And simply, I am going to write a in this way, right? So 3x2, so there are 3 equations. So do the same thing as you did here. And I am not going to write the expectations for simplicity. The rank, so by the definition, you have 2 columns. If the first column and the second column are linearly dependent, then the rank is less than 2. There is no full column rank. That is the case when beta is not identified. I told you that beta is identified when, if and only if rank equals to 2, because there are two unknowns. You need to have two rank of 2, and at the same time, if you have, so that's necessary and sufficient. So think about this. It does not work. Even if it has 3 equations for 2 unknowns, but as you see, all 3 equations reduced to are basically one equation. It is just one equation, so you don't have any equation like here. For another example, this is another example. In this case, beta 1 is identified. You know beta 1 is 1, but beta 2 is never identified. So this is another case where you lose identification. The lost identification could be about only one variable. And then let me finish up to here. So then what you can see here is the necessary and sufficient condition is so the identification relies on the rank of A matrix. A matrix is expectation of Zx prime. And first, if the number of instrument is strictly smaller than the number of endogenous variables, then that's the end of the game. Then game over. You cannot identify. So maybe you may study a little more what is still identified. Some of beta may be identified and some are not identified. But anyhow, you cannot identify, in this case, you cannot identify all beta. And if m equals to k, then we say just identified or exactly identified. You have the same number of information and the same number of unknowns. So exactly identified, and it's about the inverse matrix. So you may use the inverse matrix of A in this case. So as I said, it is equivalent to invertibility. So if it is invertible, that's it. And in our previous example, we had this in the denominator, if you remember. In one scalar case, in the denominator you had covariance between z and x, and we need to assume that the denominator is different from 0. This assumption, so relevance assumption is generalized to invertibility. So in one dimension, what you need to do here is you should be able to put this into the denominator. You should be able to divide something by this covariance. But in matrix, you should be able to have an inverse matrix. You need an inverse matrix of this matrix. And when you have more than k, and still the rank is k if the beta, so if m is greater than k, your rank may be lower than k, but if rank equals to k, then you can identify beta. But we say you are over-identified. The model is over-identified because there are some equations that may be potentially useless or potentially not used. Anyhow, you need to drop some information, or you have too many conditions than you need, and then you can satisfy. So that is the main problem, which I'm going to discuss. I will discuss that in the next video.